Okay, so today's plan, pretty straightforward. Just move on to the ratio test 11.6. Um, one note before I forget is on the Blackboard site, in the supplemental material, I posted a series review worksheet. I'm also going to post a series kind of flow chart. So taking you through a flow chart for all of these different tests and so on that we've encountered so far. There's kind of a lot of tests, and it's a little bit like integration techniques where there's a lot of integration techniques. And if you have kind of an idea of like a mental flow chart of how you want to approach a certain problem, that can be really helpful to both remember the techniques as well as um, formulate a strategy. So I'll post that as well in the next couple of days. But the series worksheet, you might want to go through and just kind of try your hand at some of the different problems. Obviously, the homework sets give you a lot of chance to practice, but if you're in the 11.6 homework set, you kind of know you're going to have to use the ratio test on all the problems. So it's a little bit less like, say, an exam situation. So if you wanted something that gives you a little bit, well, a lot less of a hint as to what test to use, take a look at that worksheet on Blackboard. The quote of the day for today is from a movie called The Truman Show. I think it was around like the early 2000s that it came out, and Jim Carrey starred in it. And the idea was that he was this guy, Truman, who was basically brought up his entire life from when he was born on the set of this, like, basically like reality TV show, except he didn't know that he was part of the show. It's this huge, enormous set, and he lived in this little town, and all of the people that he interacted with are actors, and there's cameras everywhere. So lots of really interesting kind of like ethics questions and so on. But Christoph is the guy who is the head of the show. He's the one that's behind the scenes directing everything. And at one point he makes a statement that I really liked, where he says, "We accept the reality of the world with which we're presented. It's as simple as that." And I think this really speaks to, there's a lot of questions these days about like, what's the value of education? Should we get a college degree? Is it worth it? And all of this. And I think there are tangible answers to that. So as far as, how much money you make over a lifetime, things like that, the kind of, dry answers, return on investment, things like that, the ability to go into a career field that might require a college degree if you really want to pursue that career field. So there are reasons like that. But I think a reason that's not often talked about is, really the idea of this kind of general education or liberal arts education or core curriculum. In Calc 2, we're not really in this position so much, but, you might have to take, say, an art history class or something like that. And you think, well, I want to be an engineer. Why do I have to take art? And I think the proper answer to that, people will tell you, oh, it's like mental push-ups, or, oh, it exposes you to different things, or, but I think really the idea is that each of us is presented with a certain world kind of naturally, right? Our parents, our folks, our family, um, have certain points of view. They have certain areas that they're really knowledgeable and really good at, areas that they're less knowledgeable or less good at, and areas that they basically don't know nothing about. And that's true of everybody. We have a certain neighborhood where we grew up in, certain friends that we had. Again, we're presented with a specific variety of the world, let's say, and that's the reality that we accept. And I think, it's very difficult to branch out of that on your own. It's tough to do because it's, somewhat uncomfortable and also takes time and effort. So I think that's a large part of a college degree, whether it's associates or bachelor's. I think that's a large part of that, is that idea of a core curriculum, a liberal arts background, the humanities focused, set of curricula, a general education. All of these kind of ideas touch on this importance of presenting different realities, so that when you get your degree and kind of go out into the world, you kind of have a broader basis with which to understand maybe the perspectives of other folks who were presented with different worlds and who take different realities than you. And especially in today's world where everything is so interconnected, and in a couple of seconds we can be talking with somebody on the other side of the world who has a completely different experience than us. I think that's really even more beneficial today than it ever has been. So that's what I would say is my defense of education. Of course, I'm biased. The reality of the world with which I'm presented is heavily influenced by working for a college. So, of course, take it with a grain of salt. But anyway, I think that's an important piece of the conversation that's being had a lot today. And by the way, I mean, it's an excellent movie, and I don't think I spoiled anything for you by telling you this. This is kind of like a very obvious thing from the very beginning of the movie. So, but if you get a chance to watch the movie, it's a very good movie, I thought. Okay, so absolute convergence in the ratio test. We discussed last time about absolute convergence, and we said that a series is absolutely convergent if the sum of its positive terms converges, or maybe the sum of the absolute values of its terms converges. We say that a series is conditionally convergent if the series itself converges, but the sum of its absolute values diverges. And we mentioned that if a series is absolutely convergent, then obviously it's regular convergent, but the converse is not true. We can have series that themselves are convergent, but where the sum of the absolute values diverges. And take, for example, the alternating harmonic series. 1 minus a half plus a third minus a fourth, and so on. This converges by the alternating series test, but the sum of the absolute values of the terms is just the harmonic series, which diverges. So there are convergent series that are not absolutely convergent. And we also mentioned that if a series is a positive series, then convergence and absolute convergence are equivalent. Or we could even say the same thing with a negative series. If every term is negative, the two types of convergence are equivalent. Or we could even really say the same if it's true that all terms after a certain number of terms have the same sign. So if all terms after the 100th term have the same sign, or we could say that the convergence properties are equivalent for that series as well. Okay. Give me 1 second here. Okay, so I think that's where we left off last time. So let's move on to a motivating example for the ratio test, kind of see where the details of the ratio test really come from. Let's consider the series sum n equals 1 to infinity of 2 to the n over n factorial. Let's try to evaluate this for convergence. And there might be some different approaches we could take, but one approach we could take is we could look at the ratio of a term to the next term. Or I suppose, saying more properly, the term to the previous term. So if I look at an plus 1 over an, I see that gives me 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. 2 to the n cancels and an n factorial cancels, leaving me with just 2 over n plus 1. And I note that this is less than or equal to 2/3 for n bigger than or equal to 2. So the ratio of the next term to the current term for this series is less than or equal to 2/3 for n bigger than or equal to 2. Well, what does that say about an plus 1 then? Well, an plus 1 then is less than or equal to 2/3 an. These are all positive, so multiplying through by an doesn't change the inequality. But I could keep chaining that along, right? An is less than or equal to 2/3 an minus 1. So that gives me 2/3 squared an minus 1. Or 2/3 cubed an minus 2. I can decrement the index by 1 and tack on an extra power of 2/3. And my inequalities just keep chaining along until I get 2/3 to the n minus 1 a2. And a2 I can see by just observation is 2 squared over 2, or 2. So an plus 1 is less than or equal to 2/3 to the n minus 1 times 2. So consider the series sum n equals 1 to infinity of 2/3 to the n times 2. We know this is a convergent series because it's a geometric series. Essentially, we have an extra factor of 2, and we're missing the n equals 0 term, but this is essentially a geometric series with ratio 2/3, which is between minus 1 and 1. We know this series converges, and we can make a comparison, a direct comparison with this series to show that this one also converges. So kind of roughly the idea is show that there's a bigger series that's a geometric series that converges, and then use a comparison to make the argument. Now, this isn't a formal proof, right? This won't work for like any series. There are details about the comparison test we didn't check and so on. But this gives you kind of the basic idea of what's going on here. Or really what I see is that if the limit as n goes to infinity of the ratio of the next term to the current term equals L, a real number, then basically the terms in the tails of the series, the terms in the tail of the series, kind of act like C times L to the n, right? Because an plus 1 kind of looks like L times an, which kind of looks like L squared times an minus 1, and so on. And then we could kind of compare to a geometric series with ratio L, and we know that converges if and only if absolute L is less than 1. Okay, so what does the ratio test say? Consider the series sum an, and suppose that limit n goes to infinity of absolute value of an plus 1 over an equals L, which could be a real number or infinity. If L is less than 1, I mean, L's got to be at least 0, but if L is less than 1, then the series converges absolutely. Right, note that a geometric series, if a geometric series converges, then it converges absolutely, because the kind of region of convergence, so to speak, for that ratio R is symmetric about 0, open minus 1 to 1. So if L is less than 1, then the series converges absolutely. If the limit's bigger than 1, the series diverges. Why is that? Well, that would mean that we have something that looks like a geometric series with ratio bigger than 1. So like an plus 1 is bigger than an, and then an plus 2 is bigger than an plus 1. That sounds like the divergence criterion, the test for divergence. And if L equals 1, in this case, this is a borderline case. When we start throwing around limits, a lot of times edge cases become kind of fuzzy. So if L equals 1, the test is inconclusive. The series might converge absolutely, it might converge conditionally, or it might diverge. We would have to, if we ran the ratio test, got L equals 1, we would have to look at a different test, come up with some other way of assessing the convergence of that series. So let's apply the ratio test directly to this series that we looked at before. We did kind of a hand wavy argument, but let's make it precise. So I'm interested in absolute value of an plus 1 over an. As kind of an aside, there are some other textbooks that introduce the ratio test as limit n goes to infinity of an over an plus 1. And then if that limit is bigger than 1, the series converges absolutely. If it's less than 1, it diverges. And so some folks take kind of the multiplicative inverse here. So you might look up the ratio test and say, wait, that version looks a little different than we covered. It's essentially the same theorem. It's just which way you set up this ratio. But if the next term over the current term, if that limits to a number less than 1, that means the next term looks like a number less than 1 times the current term. And when we set up that chain of inequalities, we'll have a number less than 1 to the nth power. So if you ever forget which way it goes, you can think through it like that. Or this is 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. I don't need the absolute values because everything here is positive. Again, this is 2 over n plus 1. And as n goes to infinity, this goes to 0. So the limit does exist. It's a number less than 1. So our ratio test says that we converge absolutely. And note that in this case, it would have been sufficient just to show convergence, and we would get absolute convergence kind of for free because this is a positive series. Okay, so what about a p series? Sum of 1 over n to the p. I know from previous work that this converges if p is strictly bigger than 1 and diverges otherwise. Well, what do I get from the ratio test? So an plus 1 over an. I can't really simplify this, but I know that if I take the limit as n goes to infinity, this limits to 1. In other words, it's inconclusive. The ratio test is inconclusive. This might converge, it might diverge, it might converge absolutely, it might converge conditionally. That's exactly what I would hope for, right? Because we saw with previous work that the convergence depends on the value of p. So getting an inconclusive result for a ratio test is exactly what we want. What if I look at the geometric series? Sum n equals 0 to infinity of r to the n. So the n plus first term over the nth term. Well, that just gives me absolute value of r. All of my n's went away. This obviously converges to absolute value of r as n goes to infinity. And my ratio test says if this is less than 1, converge. If it's bigger than 1, diverge. If it's equal to 1, inconclusive. So we recognize those from the geometric series work we've done before, and we would just have to look at what happens if absolute value of r equals 1, if r is negative 1 or positive 1. And in each of those situations, we could apply a different test, say the test for divergence, to argue that it diverges there. But we wouldn't get those two border cases from the ratio test. We'd have to take the r equals plus 1 and r equals minus 1 cases separately, use a different approach, and argue the convergent divergence of those separately. So one nice thing about the ratio test is for series where the terms are defined recursively like this, It actually works really nicely. So consider the series sum an where a1 is 1, and then an plus 1 is defined recursively as 1 plus 1 over n to the n times an. Does this series converge or diverge? And this would be for n bigger or equal to 1. Probably should have that in there. Well, what is an plus 1 over an? It's 1 plus 1 over n to the n. We do kind of recognize this as an indeterminate form. This goes to something like 1 to the infinity. It's a number that looks like 1 to a power, which kind of wants to be 1, but it also looks like it also kind of looks like 1 plus a tiny bit to an increasing power, which kind of wants to be infinity. But we might, in absolute values, but we can get rid of the absolute values, but we might note that this limit is actually just the number e, the exponential number 2.7 or so. This is a number bigger than 1, so this diverges by the ratio test. Any questions so far? Okay, next example. Consider the alternating harmonic series, which again, we know this converges conditionally. We argued that before. Let's apply the ratio test and see what happens here. Sum n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n. So what does this give me? This gives me negative 1 to the n plus 1 over, n plus 2 over n plus 1 times n over negative 1 to the n plus 1. The absolute values just get rid of all the negative 1 bits. So we get absolute value of n over n plus 1. And as n goes to infinity, this goes to 1. Again, our ratio test is inconclusive. And that's what we would hope. We know that this converges conditionally. If this went to a limit that was less than 1, it would converge absolutely. If it was bigger than 1, it would diverge. So getting an inconclusive ratio test is really the only option for the alternating harmonic series. Okay, and then kind of the last topic in this section is the Riemann rearrangement theorem. And this is a super interesting theorem. I don't know, I think everybody, the first time that you hear it, you think like, what the heck is going on here? But again, this is just a reminder that we have to be so careful when dealing with any kind of even quote simple operations with infinite series. So given any real number s, given some number s in R, and given a series that converges conditionally, very important that it's conditionally convergent, not absolutely convergent, then there exists a permutation of the sequence an, call it bn. So the same elements of the sequence, but in a different order, such that the series sum n equals 1 to bn. So if I rearrange sum an, if I take all the same terms but rearrange their order, if I change the ordering of sum an to make sum bn, then that series converges to S. What does this mean? It means, for example, consider the alternating harmonic series. And I think I mentioned before that this converges to log 2. But what are we saying? We're saying, what if I said, I don't want this to converge to log 2. I want to converge to pi instead. Well, to make this series converge to pi, all I have to do, in some sense, all I have to do is rearrange the terms. Now, I can't just like swap these two because, again, convergence is a characteristic of the tail. So the sum is a characteristic of the tail. So I would have to rearrange infinitely many of these terms to get it to converge to something else. But I can make it converge to pi. I could make it converge to a million. I can make it converge to negative 25 if I wanted to. I could even make it diverge if I rearrange the terms in a certain way. So if I have a conditionally convergent series, I have to be very careful about rearranging terms. We saw things before, like where if we do pretty reasonable things, like just applying, say, an associative property or something, just grouping terms a little differently in it inside of an infinite series, not in the partial sum, but in the infinite series, uh, that led to like claims like 0 = 1, right? So here's a very strange theorem, the Riemann rearrangement theorem. And a very rough overview. I was going to kind of go into a little more detail on why this works the way that it works, but I think I have um, a previous lecture recording. I think I'll probably just post that instead. But basically, the idea is to have conditional convergence. Note that if the series was a positive series, convergence would imply absolute convergence. Note also if the series was a negative series, convergence would imply absolute convergence. Or even if the series, if we went far enough in the tail, if all of the terms from that point on are positive, or if far enough in the tail, all terms were negative. In either of those cases, convergence and absolute convergence would be the same. So to have conditional convergence, a requirement to have conditional convergence, it implies that we have infinitely many positive terms and infinitely many negative terms. It also has to be true. And again, I'm doing a quick overview here. I'll post a little more in-depth discussion of this. But it also has to be true that if I looked at just the positive terms, if I got rid of all the negative terms, looked at just the positive terms, this would have to diverge. In other words, this would have to shoot off to infinity, this sum. Similarly, with the negative terms, if I got rid of all the positive terms and just looked at the negative terms, this would also have to diverge. This would have to go to minus infinity. So I can always add on more positive terms or more negative terms at my will. And when I'm adding on positive terms, I can add on as big of a positive number as I'd like, because the positive terms that are left over are all the ones in the tail, and that tail is the thing that fundamentally diverges. And when I start adding on negative terms, I can add on as many negative terms as I like because I always have infinitely many left. And I can add on as large of a negative number as I like by adding on more negative terms, because again, this tail has to diverge to minus infinity. And essentially the argument for the Riemann rearrangement theorem, it's an argument by construction. You take S, and let's just suppose S is a positive number. You add on positive terms until you get to a number that to a partial sum that is above S, and then you switch and you start adding on negative terms in the original sequence. You add on negative terms until you get to a partial sum that's below S, and then you switch and you add on positive terms again, and then you switch and add on negatives, and you kind of just zero into the partial sum this way. So that's kind of the rough idea of the Riemann rearrangement theorem. Very, very strange theorem. Now, if we have an absolutely convergent series, if we have absolute convergence, this doesn't hold. We can rearrange terms and we get the same sum, right? But for conditionally convergent series, it almost makes you ask, like, well, if we say that this number is the sum of the series, like, what does that even mean, right? It means something very specific and very technical related to all of the definitions that we've had. And again, like, if we switch some of these definitions around or loosen some of them or interpret them a little bit, interpret convergence a little bit differently, we could come up with very different answers. So there's a sense in which, like, absolutely convergent series kind of have like what feels like a real sum, and conditionally convergent series, it feels like some goofy technical statement that somehow feels like it has less fundamental meaning. I mean, that's obviously an opinion, a very subjective thing for me to say that, but at least that's kind of what it feels like to me. The conditionally convergent series, they have a sum, but for some reason it just feels like less of a true statement to say that that's a sum than for absolutely convergent series, where that sum is robust to just moving around the orders of the terms. Any questions on anything from this section? Now, kind of an aside, we want to make sure that we really understand the ratio test, because when we get to infinite series, infinitely long polynomials, so like Taylor series and Maclaurin series, when we get to those sections at the end of chapter 11, when we investigate their convergence properties, in just about every problem, we're going to use the ratio test. So when we get to Taylor series, Maclaurin series, or kind of the more general term for those series is power series, where these things are like infinitely long polynomials, if I have like a naught plus a1x plus a2x squared, and so on, I kind of see that an plus 1 over an gives me what? It's, well, let me call these b naught and this b1, b2. So bn plus 1 over bn gives me an plus 1 over an in absolute values times absolute value of x. I'd have x to the n plus 1 over x to the n. And then I can make a statement about for which values of x, for which inputs, do I get a nice convergent series from the ratio test, and for which inputs do I get divergent series. So this ratio test is a very important idea later on in chapter 11, so make sure to kind of understand it. I think it's probably one of the easier tests to perform, and it, like, I don't know, it just feels kind of satisfying when you set it up right and like a whole bunch of stuff cancels out. It's a lot more satisfying than trying to do like a comparison test, a direct comparison, and just making sure that all the goofy, are you dividing by like n minus 1 or n plus 1, and or all the inequalities pointing the right way, and getting all those nitty-gritty details right is kind of cumbersome. But I think the ratio test feels a lot more elegant when you do it. But all right, I think I'm going to end there today. I was originally planning to work through some problems on the worksheet and then post it to Blackboard, but I just posted it earlier. So work through some problems on that worksheet. Probably next week, or in a supplement, I'll take a handful of sample problems from that sheet and kind of work through them, and then and then post the answers. And then, of course, if you have any questions on any of those problems, You can shoot me an email or feel free to ask in class, and I'm happy to go over anything. Um, but again, the nice thing about that worksheet is that it's just a bunch of series, and there's not that you don't have as much information about what section it comes from and what technique you should use. So it is a little closer to something like an exam. So take a look at that worksheet. You might do that now for the next 20 minutes or so. Just go to Blackboard, check out the worksheet. And like I said, I'll post the flow chart now that we're most of the way through our, well, all the way through our specific tests. That flow chart, I think, will be helpful and kind of keep everything organized. And then when we come back, we'll start talking about power series, which is really the last kind of big topic in chapter 11. And probably the last big topic in the course. We have like kind of a quick intro to chapter 12 at the end of Calc 2. But I think hitting power series and Taylor series is really one of the big important points in Calc 2. So are there any questions on anything from today?